Good morning, everybody. We are going to continue with where I left off yesterday. So I thought I would start by briefly reviewing some key points from introducing the electromagnetic spectrum, and then go into our new topic, which is discussing the part of the EM spectrum, which is visible light. To dress for the event today, I wore, I'll show you, this t-shirt, which maybe some of you will appreciate for the fact it's actually connected to our science topic today. And also, track pants, because there's no real strict dress code here for at-home learning, right? So I moved into my closet, a little bit more space right here today. So from the few of you that responded, it looked like the video worked. So I'm going to do something similar today. I am going to start then showing you a screen like a notepad where I will make some notes as I kind of go into today's topic. All right, let's start. So I'm going to do what I did yesterday, which is show the screen. There we go. Okay. I brought this guy today too, my mascot here, for when I'm at home doing this. All right, in a variety of colors. Yay. Okay, so yesterday we started talking about, and these are just going to be notes related to yesterday too, so I have a bit of a talking point for me. We talked about, summary of yesterday. You don't have to write that part down if you don't want to. We talked about the electromagnetic spectrum, or the EM spectrum. And we talked about waves of energy. And I kind of called it all waves of light, but probably a little bit more accurately. Still not a great explanation about electromagnetism and things like that. But for those of you taking physics next year, you'll get more background there. We have different kinds of energy out there. Most of it travels in wave form, visible light being one of those pieces. So we talked about waves of energy sort of doing this. Okay. And we talked about wavelength being how long it takes you from one point on the wave to get to the same point on the next wave, whether that's crest to crest or trough to trough. Depending on the type of energy, you have different wavelengths. So radio waves are the longest wavelengths that we work with. And then gamma rays, which I thought had to be a capital G, turns out it doesn't. I'm not sure where I was going with that yesterday. Have the shortest wavelengths, and they're measurable. So the radio waves can be meters to kilometers from one crest to crest, and the gamma ones are fractions of a nanometer. And nanometer is like 10 to the minus 9, so they're quite small. This impacts the frequency with which they hit you. So anything with a long wavelength, like a radio wave, has a very low frequency because of this wave is traveling towards you, and those radio waves are being picked up and put through your radio. They're not coming at a very fast pace because it takes so long to get from one to the next. Whereas the gamma ones on the other one have a very high frequency. They are hitting very, very rapidly, many of them in the same period of time. Okay. We talked about the spectrum going all the way from gamma to radio and the ones in between. And then I try to introduce to you the idea of what some of these different waves of energy and radiation can be used for, from microwave ovens to night vision goggles to UV lights to disinfect, or your dentist might actually use the UV light to secure your braces, like get the glue to hold. There's all kinds of functions, and I left you some reading and videos to take a look at that. Okay. One thing I meant to correct yesterday, and I put it in the note, is that after we drew our nice note, this lovely note right here, that I then put this arrow in the wrong spot. So the visible light spectrum, and you'll see how this works today, is actually between the UV rays and the infrared rays. Okay, so hopefully you got that corrected. I did post a link where you can access Nelson's textbook, which maybe some of you are using or want to use. And then I'm looking for Pearson's. Apparently, that company is also opening up some access, but it doesn't seem as seamless, so I'm working on that as well. All right, so in learning about the EM spectrum in that lesson, we've sort of covered this learning goal right here, which is I will be able to describe how a piece of technology that uses light has been beneficial to society. So that's why you have the one follow-up question where you are choosing something, anything you want, and describing how that has been the most beneficial, one of the most beneficial pieces to society. So, for example, you might be arguing that microwave ovens have been the device, the piece of technology that has most benefited society. And then you're going to say why. So there's no right or wrong, it's all opinion. I'm just looking for you, which you'll see on the literacy test eventually, kind of question where you provide a response, you choose something, and then you defend your choice. So how well your logic makes sense, or any evidence you have to support your answer. Short and sweet. Okay. All right. So then today we're going to talk about the piece on the spectrum that is visible light. I'm going to put the textbook under here for just 1 second. Okay. So here's the textbook's version, one of the pages. And you can see here the gamma rays, high frequency, short wavelength, moving into X-rays, moving into UV rays, and then infrared on the other side. And this little small portion in here of visible light. The visible light is actually still in the nanometer range. So it goes from about 400 to 700 nanometers. If you watch the video I posted from NASA, it kind of explains that all these waves are flowing by us and through us all the time. But there's only this small portion here, which we can actually detect with our eye. Okay. It's really interesting in that there are some species who probably can see a little bit in here, and how fascinating that would be. Those ones that kind of have that more night vision capability. But for us, we are right in here. So all the colors you can see are within this small range here. And outside of that, you're not going to be seeing X-rays, for example. You're not going to be seeing microwaves and things like that that are flowing by us. Okay, so let's do the note, and then I'll talk some more, and then I'll leave some stuff on the classroom for you. So today, let's push that out of the way. Didn't actually write very much there. See if I can use some nice colors. We're going to talk about visible light and something called additive color theory. So I'm going to call this visible light. Okay. And we're going to do over here additive color theory. Look at that. Orange and pink go together. They're going together today. Oh, well, not much orange in there. Okay. So the idea is the white light that you see all around you actually contains all the colors of the rainbow. So when we get a rainbow in the sky, what's happening is those little water droplets that are still sitting in the air are acting like little tiny prisms, and they're taking the white light and they're splitting it into all the visible colors of light that we are able to see. Sort of like I showed you earlier on the t-shirt cover for this pretty famous Pink Floyd album. So here we have a prism, which is actually made of glass. If we were in class, I would be able to show you this. So you take this little triangular prism made of glass, and if you shoot white light into it, just regular light, natural light, you can create a rainbow out the other side. So you can take that white light and you can split it into all of these colors in the rainbow. When you see a rainbow after a storm, maybe today, it's kind of weird. Well, probably sun's not coming out today. All those little water droplets are acting like little tiny prisms, like I mentioned. And so this natural white light that we have around us is being split into this full spectrum, the full range of colors, okay, with red being on one end and violet being on the other. So I probably should have backed up here on my note, but I'll come back to it at the end. Okay, so additive color theory As we go to next is the idea is that I can generate white light by putting together what we call the primary colors of light. And some of you will be thrown because this is different than paint. It's a little bit different than what you learn in art. So remember that right now we're not talking about paint and dyes, we're talking about light. Okay, so mixing red light and green light and blue light will actually create white light. So down here, the first thing we're going to write is that in light, the primary colors of light are red, green, and blue. Okay, red, green, and blue. I hope you can see that. Additive color theory states that if you take red light and you add to it green light, and then you add to it blue light, you will get white light. And in school, we actually have like a thing that I could show you this little box that I would have like a red beam of light and then a green beam of light and then a blue green of light. And the way they would overlap in the middle would be white. So we usually draw this with a bit of a picture. So I would do a circle here. Okay, and then another circle here. See how they overlap? Like a Venn diagram. And then another circle here to overlap. Okay. And I'm going to say, and I didn't bring red today. Oh, well. Maybe I better not do that because it's not the right color. If I make this circle red light, okay, and I make this circle green light, and I make this circle blue light, think of like stage lighting, okay, when you're like shining stuff down onto the stage and you have different color filters, okay? Where they all cross over together in the middle, right here in the center, right there, it will look white. Okay, so on my shirt and in those images you've seen, the idea of as a rainbow is the white light has been scattered into the full spectrum, but you can take those three main colors and you can put them back together and recreate the white light. So we're going here with additive color theory. The idea is you add together the colors to get to white, okay, to get to the whole. Now there's some in between, there's a wide range of in between. But the main, what we call secondary colors, are the colors that you get in these pieces here. Okay, so we'll label them and then we'll list them after. So between red and green, if I just had those two and I didn't have the blue, what I would have right in here is yellow light. Okay, so with light, when you mix red and green, you get yellow. The red and the blue right here is a color called magenta, which is kind of like a purpley color, right? And then green and blue make a specific color called cyan, C-Y-A-N, which is sort of like a teal, if you know what that color looks like. It's like a greeny blue, which makes sense because they're green and blue. But you will see it on the images I share, and you will see it in the textbook too if you look that up. Okay, actually, let me help you out here. Let's put this under here for a second. This is right from your textbook. So that's magenta, that pinky purpley kind of color, yellow, and then cyan, the blue and the green making this color here. And this is what I've redrawn on your note, just without the colors. Okay, now there's other colors in the rainbow, right? If we look at this, there's a whole range. You'll know if you like do computers or you're choosing colors for stuff that there's not one kind of red. There's a bunch of different types of reds and greens and blues. They're all in here. So white light has all of them. It's just here we're talking about really basics. And if I want to recreate white, if I just use these three, I can get to white. There's also an interesting conversation we could have about what they know about people and what people actually see with their eye. And we will talk about the eye later. And colors, color blindness. Not everybody sees all of the colors that are possible to see. And they also believe there could be some people that are actually hypersensitive that maybe see more colors than the rest of us see in terms of what we can pick up with our eye. All little interesting asides. Okay, so those are the main principles for today of learning the primary colors of light. The idea that the primary colors combine to make secondary colors and altogether make white light. So here I'm just going to put a little note that secondary colors of light are yellow, magenta, and going off, cyan. Yellow, magenta, cyan. Okay. I am going to give you a gizmo. You may have forgot your password. So if that's the case, just email me or put a little message on Google and I will give you your password. It's going to be all about this, practicing this. One thing you're going to learn on there through that simulation, if you're able to do it, is that there's like full red and then there's obviously not full red. And depending on how much red and how much green your colors have, you're going to get different variations of colors. It's kind of going to mimic sort of like the old TV style or the computer screen idea, where basically there's red, green, and blue tubes. And depending on how much power you put to those different colors, you can create all of the colors. The red, green, and blue on full will give you white, but that you can tweak how much red and how much blue and how much green and make things like pink and orange and all those other things that show up on a computer screen or on a TV. And that's kind of how your eye works as well. For those of us that have full vision that aren't in any way color deficient or color blind, you have 3 different receptors in your eye, which we'll talk about later: red, green, and blue. And that helps you see all of the colors in the rainbow. Okay. The last part I'm going to sort of introduce to you today, some of you would have learned about colors in the rainbow probably at some point in elementary school, and might have learned about Roy G. Biv and the idea of going from red to violet. So I'm just going to add this down here at the end. The rainbow. Okay. Rainbow contains all of the colors that are in white light. And Roy G. Biv goes like this. Let's hope I do this right. Roy, oh, see, I did it wrong. Roy G. Biv, ROYGBIV. And this stands for, if you look at, let's see if I can put it there at the same time. Red, orange, yellow, green, blue, indigo, which is sort of like that blue color, violet, which is the purple. So rainbow always comes out split like this. There's a reason why that is. And you can see here the colors that go with each of them. So these ones here in the purple have a wavelength of about 400 nanometers, and the red is about 700 nanometers. So purple or violet has wavelengths to the light of about 400 nanometers. That's how far it is from crest to crest. And the red is 700 nanometers. And these are, and all the in-betweens of these are somewhere in between here. When we talked about the EM spectrum yesterday, I told you that it fits between infrared and ultraviolet. So if we just look at this for a second, here is red. And beside this, if we went outside of the visible light range, is where you get into infrared. okay? And then over here on the other side of violet, is where you get into ultraviolet or UV. So it fits right in here, and it makes sense if you look at what's on either side, how that would make sense. So once you get outside the visible light of red, you move into what we call the infrared, okay, where we talked about night vision and thermal and being able to see things from heat, stuff like that. And then if you go outside of violet, you get into ultraviolet, which is UV, and although you can't see it, what that looks like from the sun. Okay, so there's probably more things I can say, but I'm probably pushing the limits of how long I want to make these videos to make all the work I leave you doable. Remember that it's 3 hours total work, so if I'm somehow misjudging and giving you too much, or for some reason it seems like too little, maybe not enough explanation, feel free to let me know in comments and communicate that to me, please. So what I'm going to attach to this is Gizmo, so that you can work around with colors and see how when you put different colors of light together, what you get. Remember, it's not paint or dyes. That's going to be a subject of another bit. It's probably most of our content for this week. It happens to be a long weekend. Forgot about that. So Friday and Monday are holidays. I will put an office hour up for tomorrow. So I'm just trying to think what I want to remember to say. The purpose of the office hour is to have a chance to talk to each other. I love the chance to talk to you guys. This feels pretty isolating. So any chance I get to see your faces or hear your voices or interact, I would actually really, really appreciate. So I think I'm going to pick 10 to 11 tomorrow. It's pretty random. I don't know what kind of hours you're keeping. If that ends up being a bad time, please let me know and I can pick a different hour. I will invite you to a Google Meet. And that way we can come on together. We can talk about the science from this week. We can also just check up with each other. You don't have to stay. You can come on, get off, but it'll give you an opportunity to ask me questions and for us to check in with each other. So there won't be any new material tomorrow. I'll just do the office hour tomorrow, which is Thursday. And then I will probably, towards the end of the day, Thursday, well, we'll see what time I get it on Thursday, put in a couple questions, like a Google quiz thing on your class, just to see if you've got the main ideas from this week. So I told you yesterday was all about learning about the EM spectrum and technologies we have as a result of taking or capturing and utilizing the fact that those waves exist, those different forms of energy exist. Now we're working on sort of sources of light and the phenomenon that we see because of light, like rainbows and this theater lighting and TVs and computer screens with this additive color theory or eye. All these things about how we see the colors we see and what we can pick up in that tiny piece of the EM spectrum. Okay. So I'll try and put some questions on that just check in with your understanding so far. But I'll do that after the office hour in case you want to talk before that. What else? If you wanted to read about additive color textbook, like additive color theory in your textbook, and you have your textbook, it's on page 386, 387. The Nelson one doesn't really have as much. There's a little bit on page 467. That's the online one I've shared so far. But you can take a look. It's really brief. I don't think it's actually that helpful, but it is there if you want to look at it. And I think that's where I'm going to end for now. So I'll leave it at that, and I'll see if you have any questions that come for me later. Okay. It's really helpful if you confirm that you can see these things or what's working and what's not working. If you feel you can do that. All right. Okay, so I will be available tomorrow, 10 to 11. You'll see an invite later, and hopefully we'll Google Meet. All right. Take care. Oh, wait. You're probably going to have to watch me shut this down for a second. I apologize. And yes.